Hello, students. We're going to talk about heat transfer today. There's the three main things: convection, conduction, and radiation. And we're going to ignore this, not because it doesn't exist, but because it is difficult. When we talk about convection, what it is a fluid flow of heat. So we have a fluid, say it's air, and we have two surfaces at different temperatures, and there's conduction between the air and one surface, and then that air moves, and there's conduction between the air and the other surface. So we're going to ignore convection as it's difficult, as it's fluid flow. So we're going to focus on conduction for this video, and then we'll do radiation in the next video. So let's show what's going on. We have an environment. So, draw trees and birds, and this is, say, minus 5 degrees Celsius outside, so there's snow on the ground. And then we have the wall of your house, and then you're in your house, and it's 20 degrees Celsius. So heat is going to go through this wall. It has to. All right, no matter how insulated it is, it has to go through it. And what's important is, from the point of view of, say your parents who are paying your electric bill, the heat has to leave the house as slow as possible so that they don't have to replace the heat that's lost in their environment in the house. So we're going to look at a problem that looks at this, but the gist of it is, the larger this wall is in surface area, the more energy leaks out. And so let's talk about the power. And it's going to be, well, it depends on the area. It depends on the differences in temperature. If there's more energy on one side of the object than the other, then it's going to be pushed through faster. It depends on the length, the thickness here, but it's inversely proportional. If you have to push through more stuff, then it's harder for it to get through it. And then it depends on the actual material you're pushing through. I've done that poorly, excuse me. There we go. It depends on a constant. And this constant you can find on page 572. It is a material constant, what's called the thermal conductivity. Thermal conductivity. All right, is K. All right, so we're going to go and do an example problem. So 5 degrees Celsius outside. So we have our environment we drew. Not too many seagulls out at 5 degrees Celsius. Actually, you've seen this. So 5 degrees Celsius, glass, and it's going to be 1/4 inch thick, so 6 millimeters thick. And the area of it, this is going to be a box that is 1 meter squared. And the inside room is going to be 25 degrees Celsius. I'm not good at these tablets yet. So we're going to look at this like your parents might look at it, which is, how much am I going to have to pay to keep the house at 25 degrees Celsius when it's 5 degrees outside? Actually, What we wanted was -5. We wanted it to be really cold. So delta T here is 30 degrees. Right? And so let's look at the power we're going to use. The power is, and of course the power will be the heat divided by the time eventually. So we can figure out how much heat we're buying. But the power here, well, we look up for glass. And we'll have this K function is 0.8 watts per meter degree Celsius. Then we'll have the area is 1 meter squared. And we'll have the change in temperature is going to be 30 degrees Celsius. And our distance is going to be 0.006 meters because it's 6 millimeters. So 0.8 times 30 divided by 0.006 is, lucky numbers, 4,000 watts. So what I want you to imagine here is, you know what a microwave is like, or a hairdryer, something that's about 1,500 watts. Imagine having 3 of those running nonstop. That's what this house that's at 25 degrees Celsius has to do for the energy to go out into the environment at -5 degrees Celsius. So the total heat is power times time. And so the heat, say in 1 day, we're going to do 4,000 watts times 86,400 seconds, and that is 3.5 times 10 to the 8 joules. That doesn't seem like a cognizant number. Like, it's hard to think of it. So we're going to go and look at how you buy electricity. So a kilowatt hour is literally the gist of it is use 1,000 joules per second over a period of 3,600 seconds. 3.6 times 10 to the 6 joules. So that's our kilowatt hour. Now, in our problem, if the power is 4,000 watts, then Q for 1 hour is 4 kilowatt hours. And you buy your electricity from the electric company at some rate, say 0.09 per kilowatt hour. So this is 4 times 0.09 is 36 cents. All right. Now, what we're describing is one window. For each window that is built like this with one piece of glass, it costs you 36 cents to let heat escape through it every hour. That's why your electric bill is so high. So how do we solve that? Well, what we do is we make insulation happen. For a window, we do glass, air, and then we have double paned windows, and so it has to go through air that's at some intermediate temperature, and that lets you do nice things like use the air as insulation, or it lets you do things like fill it in, like the walls of your house, fill it in with something that leaves material that are not conductors of heat. So let's review a minute here. This thing that I'd said, power is Ka delta T over L. Really, this is power is this conductivity times the area times a derivative, dt dx. And this is always true. You can figure out the temperature at any point in the glass in your window. And so what we could do is plot, and what we'll plot is the temperature and the location, L. And so, all right, this first part is minus 5 degrees Celsius. And then when you get to the glass, it jumps up. And it jumps up to 20 degrees Celsius. And this thickness here is 6 millimeters. And then inside, or actually, yeah, this is 25. So at 25 degrees Celsius in the room, then it goes on like air. So in principle, you're finding a temperature profile. And, oops, undo that. And do this. Yeah. Okay. So, come on, computer. So this slope is dt dx. And it's true no matter what. The other slopes are too, but these other slopes are 0 since there's no interface, there's no surfaces. So in your homework, 1 and 2 are dealing with problems like this. And I do want to talk about the double paned windows a bit, is what happens if you do have that. So say this is 6 millimeter, and then this is 6 millimeter, and in this area in here is 12 millimeter of air. And then so it's minus 5 and 25. So this, if I plotted it, would look like where this is not 0. It would go up, and then it would go up really slowly, and then it would go up again through the other glass. So the idea is that we could ask, what is the temperature in the air? And the way we do that is to set up how much power is leaking through each pane of glass. So if we call this glass 1 and glass 2, then we can find power 1 is Ka over L. And it's going to be based on temperature of the air minus 5 degrees Celsius. And we can do power 2 is Ka over L. And we'll have 25 degrees Celsius minus the air temperature. Right? This is one of those cases where delta T is T hot minus T cold. And it's really just absolute values, big number minus little number. But the point of it is that the power that goes through here, P2, has to equal the power that goes through here. If it didn't, the air temperature wouldn't be constant in here. So these things have to be equal, and so you can solve for the air temperature. So you can solve for that. And for something like this, you can estimate in the middle of the air, it's going to be 25 minus 15 is 10 degrees Celsius. The middle of the window, it's about 10 degrees Celsius. If you touch a window, it's cold because it's colder than the room you're in. It's colder than you are. All right, so the first couple of questions in this homework, 1 and 2, are like that, talking about. Number 3 is a little different. What happens if you have 2 different materials? Here we have a sandwich of three, but you could just have two materials and ask what is it at the steady state point in the middle? What is a junction? It's the same math. You're just saying the temperature at a junction is based on the power going through the gold versus the power going through the silver. Okay, so next video, we're going to do radiation. For these videos, I realize they're kind of, to get all the information in, they're dense. If you have questions, please email me about them.